Hi everyone, this is Augie. This is one of the videos that I do that are part of the Augie's Tech Corner. And the reason for this video is because I recently saw a video of somebody placing an antenna next to a carbon frame. Okay, and I don't think that he was meant to that. He was just showing the how to use this Velcro strap to hold the antenna, but I bet he's a pretty knowledgeable guy, so he probably doesn't make this mistake in the actual installation. So so the problem here in the antenna is that it's close to the carbon frame. Antennas, and by the way, this is a coaxial, and this strip shield on the outside gives this element here that has inside the center conductor and outside has the dielectric, plastic. This is the actual active element of the antenna. So in order to show you what that does, I made a solid model of antenna, as you can see here. This here is the center conductor. Okay, that would be the center metal inside the coaxial. Then we have the dielectric, which is this here. Okay, and then we have the copper, or well, in this case, they're actually copper. They're plated, so they seem to be silver, but they're inside. They are actually copper. So this is the copper shield around it, and then this is the insulator, the outer insulator of the antenna. So that's the way this works. So you have so now the question is, okay, so what is the length of that? The length of this piece here. This is going to be a quarter wave. So in other words, the distance between this spot here and this spot here is going to be about 30.6, 31 millimeters, something like that. Okay. And the reason for that is because you have the speed of light, which is 300,000 meters times 1,000 is millimeters, divided by 2.4 gigahertz. You get 125 millimeters long. That's a full wave. And then you take that and divide by 4, and you get 31.25. But it doesn't matter. So that's 31.25 should be the correct measurement. But I already did this model in a simulator. So the reason why I did this model is because I can use this model, okay, and use it on electromagnetic simulation. Okay, and this model includes the ground plane of the receiver. So the receiver or the flavorless unit or whatever you're using will have a ground plane in the PC board to which this connects to. Okay, so we can see it here. So this copper here is connected to this ground plane. Okay, and this is the center conductor, as you can see. The dielectric is semi-transparent, and that's why you can see it here. Okay, so we have this solid model that we're going to use. And notice that this is a ground plane, but it's actually a finite plane, meaning it's not really large, it's actually small. So it is not really a good ground plane. But that's just the nature of the receivers and all those things. So that will have different consequences regarding when you design something like this. But let's assume that they know what they're doing and they design it correctly, right? So now let's bring, okay, so here we have an electromagnetic simulator, and I brought the solid models here, okay, and I assign then the materials. For instance, I assign copper to the conductor, the center conductor on the outside, okay, and it will have 58 million Siemens per meter of conductivity. Very, very good conductor. Okay, and you have the material inside is a PTFE, is a kind of plastic. Okay, so material for the PTFE is going to have 2.1 Siemens. No, sorry, this is going to be lost permittivity, not conductivity. So 2.1 is that dielectric constant of the PTFE, which is Teflon, plastic, and it has a low loss time. It's a low loss dielectric constant. That's why it's used for the insulator of this part here, so that when it travels through the coaxial wire, it has low losses. Okay, same with so in other words, you define the materials and the geometries and things like that, and then you put it into a simulator, right? So that simulator will have will give you a result, right? And the result for this here, I actually did two simulations. This one here, and let me bring the other one here, which is going to be this one with the carbon plate next to it. Okay, so we're gonna see what the antenna gain is when it's with a carbon plate and without the carbon plate. So that way you will see how dramatic the effect is. Okay, so this one is the first one, so let's bring that again. So I'm going to run that, and it's already loaded here. I have number one simulation here. It's going to be the one without the carbon, and the second simulation here is going to be with the carbon. So with the carbon here, this is what we get. So let me first go full. Okay, so what you see here is actually the loads, the behavior of the gain. This is a gain, and as you can see, the colors here indicate the gain, right? So like purple and really deep purple is minus 30, which is, by the way, 30 is in dBs, dBi is actually, and 30 means 1,000 times smaller. In other words, if the this antenna receives, let me turn this into transparent so you can see. If this antenna receives, is pointing exactly towards the transmitter, it will actually attenuate the signal by 30 dB. That's 1,000 times the signal. So whatever you're transmitting is going to listen to that signal, and it's going to attenuate it by 1,000 times, and that will give you 30 dBs less of gain. So obviously you want to be, as you can see here, here's the transmitting element or receiving element, depending on which one it is doing at the moment. You're going to have a pattern that is dependent on the orientation of antenna. So because this antenna is mounted on a wire that is mounted on a small ground plane, the ground plane effect is not too large, and that's why the antenna, instead of being like a donut, it has this shape here that you have, right? And this shape is because of the small ground plane. So you have the actual shape is, as you can see, this one here. This is the shape of the pattern. Normally this will be a circle here and another circle here, but because it is not an infinite sized ground plane, then you have this deformation. And also notice also that the maximum gain is not actually across horizontal, but in a cone shape, so around here, this whole area. So what if you look at this in a, let me see if I can, no, gain of theta 3, okay. So see this vertical axis here, the vertical axis is actually zero. Zero is on the top, 90, 180, 270, and 360, okay? So zero is here. And as you can see these are different frequencies, so it has different responses. And so as you can see, this scale is 6 dBs, okay? Mostly because this one goes around that area, right? See, the maximum is 4.41. By the way, the ideal gain of a monopole is the gain of the dipole plus 3. So double the gain of the dipole. But it changes the impedance, So a dipole ideal is 2.15, and a monopole ideal would be 3 dBs more, so 5.25. I'm sorry, 3.21. I'm sorry. No, 2.15. I'm sorry. So and then the ideal monopole would be 5.15. Correct. But because it's real life, that's why it doesn't go all the way to 5. We have 4.41 here, the maximum. Okay. And as you can see, whenever I move it, here's 4.3 from stuff like that. If I go here, it's going to be -2. Here's going to be -12, and over here is going to be 0, which is it receives exactly what it's getting transmitted. So so if you look, like I said, this is vertical, becomes horizontal here. So we have, as you can see, this shape here, this shape like that. This is exactly the shape like this here. Okay. So that shape shows you the gain, So as you go towards either one, either the top or the bottom, you will have very bad reception. That is the reason why they put one vertical and one horizontal, because once you have one horizontal, then the other receiver antenna will have these lobes in the direction where this one has the nulls. These are called nulls of an antenna. This is a null and this is a null. Okay, this is maximum lobe here, and so that's why they put one horizontal and one vertical. So that if this one doesn't catch it, well, the one that is at 90 degrees will catch it. That's why it's called diversity. Diversity is they have 2 or more receivers that will be selected according to the quality of the signal that they are receiving. And that's why they usually use 2 antennas in a high frequency application like 2.4 gigahertz. Back in the day when there were 72 megahertz, you don't need that because 72 megahertz is not as directional as 2.4 gigahertz. So pretty much anything will catch the signal without any problem. But because of these microwave-like frequencies, they behave a lot more like light. In other words, there's shadows and things like that that can affect the transmission. Now, as you can see, you have pretty much around the whole thing, as you can see, it's a circular. And because it is in the air, open air, and it will have a behavior that is radial. Now, let's see what happens with simulation. And what we do is we bring the carbon fiber plate and we put it here. Oops, where's that? Okay. We put the carbon fiber plate here behind the antenna, close to the antenna, like in that in the picture that we saw, like this, right? It's close to the carbon. And you will see how the antenna is going to be affected by that. Okay, so let's bring the simulation again. Okay, so let's turn this one off for a second. Okay, and where's that? Would be that one. Okay, so now we have here the simulation of the antenna and receiver with when they are located next to a carbon plate. Carbon plate it's not fully conductive, it's not like copper, but it's conductive enough to resonate with the waves. and will therefore affect the performance of the antenna. So let me turn off the visibility. It's still present, but it's not going to be visible. Set to invisible, okay? Because I want to show you what that looks like, okay? So let's bring this other one now and look at this thing, okay? As a comparison, let me show you the other one. See how much smaller it is. And if you look at, let me hold on for a second. Let me show you what. If you look at what it looks like, okay. Let's see if I can show you. So this is the back, as you can see. That's the back, and it has a null there, and it's very, 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 very bad. And it's exactly the same antenna. The only difference is that it was placed next to a carbon plate, in this case a frame on a helicopter. But notice that the colors on this thing, look at how the one there, minus 16, so no matter where you go, it's going to be very, very low. So it's going to have an effect on the, like 20 is 100 times less, 10 is 10 times less, 30 is 1,000 times less. So there will be locations where it's, so no matter where you go with this, it will have a very bad reception. And so let me see here. Okay, so this is in comparison, So this is exactly the same as here, same scale. And as you can see, where you had 4 or 6 or I'm sorry, 4.48 or something like that. Now over here you have now like minus 15. The best case, minus. Let's see about here, probably minus 14. Minus 14 is still a lot. I mean, let's calculate what that is. So minus 14 will be 14 divided by 10. Okay, 1.4. Negative, of course, because it's minus. And then we raise 10 to that, and it will be this much, which is 25 times less. Okay, so 25 times, take the log of that, okay, and multiply by 10 times 10, and that's exactly the dBs that we are losing here. So even the best location, the 14, something like that, minus 14, is going to still divide or attenuate the signal 25 times. So when you do this, these antennas and place them close like that, that is exactly what you're doing. You're making something that could have a good reception into something that it just simply doesn't work. And the proof is, compare the two, Look at that. Oh, another thing that is interesting, let's turn on the visibility of the carbon plate, and you will notice that the set visible, okay? So you will notice now that the very minimum is actually behind, which makes sense, behind the carbon plate, and the little bit of gain, actually the less attenuation that you have is on the front, but still it's very, very bad. So as a result, the recommendation is do not do this, do not add antennas that are next to the carbon plates or any conductor whatsoever, whether it's that or some metal thing next to an engine, anything that can conduct electricity, because it will have this effect. And this effect is actually variable, and this is the worst. And the worst thing is that because you have something that is in the wind and is switching and changing. So because of that, you are going to have a variable gain. In other words, the wind moving antenna will have an amplitude modulation of the signal that will increase the error rate of the QAM demodulation. Okay, so uh, so you need to minimize that so you have enough gain all the time. And don't forget, that's like I explained before, the reason why you want to have two antennas as a diversity in 90-degree configurations is because these nulls that are exactly the ones that are pointing towards where the antenna is pointing towards, you want them to be covered by the other 90-degree antenna presenting its maximum reception towards the location that this one is pointing toward. So you want that to be this null here covered by an antenna that when placed horizontally, for instance, will have these lobes directed in this direction. Okay, so that's it. That's pretty much what I wanted to show you guys. And hopefully you guys are never going to do that again. Don't do that. Don't put those antennas next to any conductive surfaces because it does this situation. And okay, so hope you guys liked it. Please click on subscribe and like the video and all that so that we can get this promote the video so people learn this and they have less problems with their RC models. Okay. All right. Thank you. Bye bye.